Yeah, as Anna mentioned, we do quite a fair bit of different things in this lab here in Wollongong. And first, yeah, I want to say I'm connecting. We're all in different part of Australia, I guess. I'm connecting from Darawal, beautiful Darawal country today. So I just want to pay my respect to the traditional custodian of this land. And here on this Darawal country, we do work all across Australia and all across the world in a whole range of discipline. With Uri, we've been working up in the Flinders, looking at 800 million years old rock to learn about the origin of complex life. With Patrice, he sent me pretty much every sediment from around Australia to analyze for strontium isotope, and with a lot of exciting potential application. And we even do stuff in medical research, zapping a mouse brain sections with a laser. It's very fun. But I'm not going to talk about mice today. I don't think no one will care that much. I would talk about regulate. And on the right, that's in yellow, that's all the aspect system we do in the lab here. So covering a little bit of the periodic table, but you always have people coming and say, oh, can you measure this isotopic system? And of course we don't. And it's pretty annoying when you realize that you never do enough. You always have people who want to do something you don't already do. So talking about the critical zone, that's a term, I guess, the American community coined about 20 years ago already. And of course, that it is a critical zone for all life on the planet, including us, and defined as going from the bedrock to the top of the tree canopy. And as you see on the right, that's the figure I borrowed from their website. That's covering a lot of different disciplines in the scientific community, geochemistry being one of them, but there's a lot of different disciplines involved. So that's pretty much the epitome of interdisciplinarity, where you have all scientific expertise coming together. In the US, historically, they have more and more what is called critical zone observatories. And today, I think there's probably about a dozen. And over the years, with my American colleagues, I've been actually involved in quite a few of those, couple in California, on the East Coast, and different sites in Puerto Rico. But since there's been there's been observatories that develop in other places, like in France, in India, and I know, and Uri and others have been talking about that. Hopefully, I'm not spilling any beans, but talking about having the same sort of observatories in Australia, which I think we really need to have, because obviously our environment is completely different from the US. Even if that wasn't just to fill some of the gaps that the American observatories leave, we need to also address our very unique environment. Some of the tools, again, I'm trying to keep this brief. So some of the tools I've been using is to use a chronometer for solar processes, and using what we call uranium series isotope. And that's looking at the decay chain of uranium, starting, this one is uranium-238, and we generally focus on the top of the chain, just looking at this one, uranium-234, thorium-230, and sometimes radium-226. And the idea is that these isotope ratio, they vary as a function of the chemical weathering process occurring in the soil, and also as a function of time, where you can see in some weathering profile a really nice linear evolution with that ratio deviating from a value of 1 in the bedrock into a value less or greater than 1, depending which isotopic system are you looking at. And that can give us an idea. So if you collect different samples, so sample A, sample B today, we can use that chronometers to define what we call a weathering age. It's telling us basically the amount of time that elapsed since the weathering front was at that given depth. So you can see that if I go back in time for that sample B, of course, the weathering front would have been at that depth at a much more recent time than looking at sample A. So as you decrease with depth, you should get older and older samples, and older meaning an older weathering age, a greater amount of time since the weathering front was at that given depth. And then use these model weathering ages to also derive regulate production rate. So how quickly that weathering front is propagating into the parent material. And that's been applied. So that's been applied to critical zone observatories in the US and a couple of different sites, in particular in Puerto Rico, one developed on granodiorite, another one developed on volcanic clastic sedimentary rocks, but also in sites around the world, including in Australia. So we applied that first actually in southeastern Australia, in the south coast of New South Wales, near Bega, on the escarpment west of Bega, and also different sites in New South Wales. And not going through all these details of each study, but really compiling that, and that's something we did in a paper about 10 years ago. When we were looking at that site in Puerto Rico that's developed on volcanic clastic sedimentary rock, we found regulate production rates that were much faster, up to an order of magnitude faster than what's been found around. And compiling what has been done in those different studies, you also see that, well, if you compare at least the same sort of parent materials, granitic parent material, you see that climate doesn't seem to have such a strong effect on the weathering rate, on the production rate of these regolates, which is a little bit surprising. But what is less surprising is that the type of parent material, and having these volcanic clastic rock, which are ground up sedimentary rock, but ground up volcanic material, weather a lot faster than granitic parent material under the same type of climate. But also another result from that is that the range of production rate, of soil production rate, which is in yellow here on the right, is much narrower than the range of erosion rate that we measure across the world. So in some cases, that means that, well, you have landscape where, of course, that regolith is developing, is thickening, and mostly in lowland areas, whereas you have alpine region where the erosion rate far exceeds the production rate, which explains this bare rock landscape, but also which is much more concerning when you look at erosion rate associated to agriculture, where we are, of course, as we know, stripping the soil we need to sustain our communities. And also, yeah, still in the regulate, but at a much smaller scale. I thought I'll just mention, some of the work that we did on weathering runs. So we're looking at a micrometer scale of weathering, the sort of information we get at the scale of the weathering profile. So you're talking centimeters, meters. You can also get very detailed information, and that's a piece of weathered basalt that was collected and sampled. And you see, of course, that weathering rind that develops from the pristine core of basalt. And using laser ablation, you can map that pack of weathered rock for all sorts of different elements that you'd like to map, but then also study and elucidate how fast and how much of each chemical element are removed from the parent material and from the weathering profile. And similarly, as I showed the scale of the weathering profile, At the micrometer scale, you can also measure U-series isotope and get the sort of information in terms of weathering rates and development of those weathering rinds. But going beyond the weathering profile, we can actually use these tools to learn a little bit also about erosion. And the reason for that is because of what's happening in U-series isotope in weathering profile. And for instance, if we look at uranium-234, 238, we see that generally that ratio decreases with decreasing depth. And then we can start using that in fluvial sediment as a marker of the erosion that's happening at the catchment scale. So you would predict that if you have slope-walk erosion, for instance, dominating in the catchment, you would have a ratio because you're sampling just the top of the weathering profiles with a low isotope ratio. You would have a ratio that is lower than a catchment where you have mass wasting dominating, like deep landslide, where you're going to mix up stuff with different isotope ratio, but dilute those low values with something that has much higher values. And then we can combine that. So let's not just talk about uranium isotope. We can combine that with other isotopic systems like lithium isotope, which are quite useful because they have a fairly narrow range of isotopic composition in different types of parent material. And they fractionate during clay formation, whereas lithium-6 likes to stay in the secondary minerals, whereas lithium-7 like to bugger off into solution. So then you can use the lithium isotope composition of sediment, and especially interesting going back in time looking at sediment deposit, where a decrease in delta-7 lithium tells you about increased soil formation and landscape stability. And then, yeah, so why look at that and why look at that back in time, looking at sediment deposit? Try to understand how that balance between soil erosion from uranium isotope and production from lithium isotope change over time in response to quaternary climate variability. So how do you go from one type of landscape to another? Why do you want to look at that? Well, because of course, as we know in the past, the depletion of soil resource have been one of the contributing factor to the fall of past civilizations. So we don't want to end up like these guys. And an example of a study we did a few years ago in the lake at the border of Northern Macedonia and Greece, Lake Dorian. So we look at sediment going back, so covering the Holocene, so covering the last 12,000 years. And what we saw was quite interesting. Those gray bands are basically colder events. You have your younger Dryas, but also colder and drier events at 8,000 years and 4,000 years. And you see that uranium isotope are basically following climate variability. As you would expect, that erosion is really in sync with climate variability. When it's colder and drier, you have shallow erosion. When it's wetter, the erosion can dig deeper into the landscape. What we got from lithium isotope is completely different. You can see that it's very much ignoring those shorter, cold, dry events at 4,000 and 8,000 years. What you see is that at the end of Younger Dryas, which was the last major cold period, you start having lower and lower and lower lithium isotope value, telling you you have clay formation, you have soil development. So your landscape is fairly stable and you have this soil developing. And then everything changed after 4,000 years, where we see one, the uranium isotope are telling us you have deep erosion, and lithium isotope are telling us what you're putting in the river, it's basically bedrock. There's no clay whatsoever. So that sync between the two isotopic systems is showing us something you don't see for the previous 8,000 years. It's the deepest erosion event you see in 12,000 years. And that we associated that to deforestation in what was Macedonia at the time. And looking at the archaeology and looking at record of the past, we know that the timber in Macedonia was actually of very high value. They were using that to build ships. So they probably completely deforested that area, which drove that massive erosion event, which drove also, interestingly, that happens just before what is known in Greek prehistory as Dark Ages, a time of widespread famine across Greece. So maybe this sort of early human-driven environmental catastrophes were also the first one driving social consequences for communities. And then another study conducted in the same region on Lake Ohrid, at the border of Albania, Northern Macedonia, and Greece. What we found, so looking at about the same period of time and just looking at uranium isotope, we found also something interesting where for the first 8,000 years, between 8 and 16,000 years, there's a good sync again between erosion and climate. When it's getting drier and colder, you have shallow erosion, so you have depleted uranium isotope value. When it's a little bit warmer and wetter, you have deeper erosion. But what we see after 8,000 years, between 0 and 8,000 years, is completely different. It's very little variation. We have very shallow erosion for the rest of the record, despite climate variability still happening. And the way we understand that is that what is changing at 8,000 years is the tree cover. After that time, over 80% of the catchment are covered in trees. So that's, for us, it's highlighting the role of vegetation in, yes, stabilizing the landscape, but also disconnecting soil erosion from the response, the sync with climate variability. And then application, we started looking at application of other isotopic systems like boron isotope to look into understanding past fire regime. And again, the end game here being, well, again, looking at the past to understand how fire regime in Australia changed in response to climate variability, which could inform us to better predict future change in fire regime. The reason to use boron isotope, we could talk about other isotopic systems like that, but boron is one of them that is strongly cycled through vegetation, and during that cycling, you have isotopic fractionation. So the rationale was that, well, if you remove the vegetation, through a bushfire being an example, then that will change the isotopic composition of the clays that are going to be neoformed in your soil. And we've tested that experimentally, where one of my PhD students put some eucalyptus in a furnace at different temperature, and then mix that with rainwater, mix that rainwater with soil clays, and look at the composition of the clays. And what we found is that the composition of the clays was actually changing depending on the temperature of combustion of the bark that we combusted. So there is a signal that is recorded in the clays. And then we've tested that on natural sites. So one of them here on the top left, that's Yango National Park, just north of Sydney, but also that map here in the middle, that's several soil sites in the Blue Mountains. And what we see, as we predicted and as we observed in the experimental work, is that where you have high severity fire, so LL, LH, HH, that's different sequence of fire severity. LL meaning that you had two low severity fires following each other. LH meaning you had low severity fire followed by high severity fire. High severity means it burns all the way to the top of the canopy. So where we have high severity 5, we do record the different signatures in the clays with a higher boron isotope composition. So then we can start, and we start looking in sediment deposit to apply that and learn about past fire regime. And also, yeah, I wouldn't cover all the isotopic system that could be used for that, but just referring you to a paper that was published already 20 years ago. They also look at other isotopic systems like magnesium and calcium isotope that do fractionate in plants, that do fractionate during chemical weathering. And there are many others like silicon isotope also have been used. And then almost to a final word, we've been doing some projects with indigenous communities looking at the effect of cultural burning on soil health. So that doesn't really have to do with isotope, but it doesn't have to do with isotope all the time. We've just been looking at the physical and chemical properties of the soil, things like soil pH and density and so on. And we compared hazard reduction burns and cultural burns, and we found that actually we found rationalized with our Western knowledge system that we call science, rationalize the way we understand as non-Indigenous people, something Indigenous communities have known for thousands of years. So that concept of soil health, I think it's quite interesting, and I'll be keen to hear from people here if they have any ideas on that. Because also, and I'll finish on that, a colleague of mine pointed out recently that paper that came out from the UK, where they define what they call soil health benchmarks, and they have these tools. If I switch maybe to my browser. If that loads. But they define this sort of benchmark to help people who are not soil scientists, like me, to understand what is a healthy soil and how the soil in their area is doing against those benchmarks. So I wonder if that's something that exists, if that doesn't exist in Australia, whether if something the community should consider developing too. Not that, as a Frenchman, I'm not going to tell you we should imitate our British friends, but that's just an idea. Yeah. And yeah, that's it for me. Thanks.